Howdy Bike 410 students. All right, so enzyme activity can be influenced by the concentration of enzyme that you start with. Obviously, at a given enzyme concentration, increasing substrate concentration is going to matter until you saturate the enzyme. But it can also be influenced by other things, such as pH. At extremes of pH, you can actually destroy the enzyme, right? If you unfold the enzyme or if you protonate an important residue in the active site, like if the histidine can't lose its proton, it can't act in that first step of base catalysis in order to make the nucleophilic oxygen on the serine, right? So pH is one way to perturb an enzyme catalyzed reaction. It can also affect the substrate, so your pH can be detrimental to the enzyme catalysis rate, not only from the point of view of the enzyme, its active site or its folding, but also from the point of view of the substrate, which could be protonated or deprotonated and therefore no longer bind to the enzyme, right? So the effects of pH could be due to an effect on binding or catalysis or both, right? Temperature is also a variable that can affect the activity of an enzyme. It turns out that enzyme activity increases with increasing temperature, mostly because you're increasing the movement of molecules of substrate around the enzyme, so that just by diffusion you can actually have more encounters when you have more motion, right? So you can increase the rate of catalysis with increasing temperature, but at temperatures that are higher, say above 50 to 60 degrees Celsius, typically, or it really depends on the stability of your protein, you see a drastic decline in enzyme activity. So we're looking at two effects of temperature. You can increase the rate, typically doubling the rate for every 10 degrees, as long as your enzyme is stable and active. But then at higher temperatures, the protein begins to denature. You may destabilize important interactions like that aspartate in the active site may not be able to orient the histidine. Or you can have an overall unfolding of your protein so that none of the protein can fold to bring those active site residues together, right? So if you lose structure, you lose function. So those are the dual effects of temperature on enzymes. But you can also affect an enzyme under its normal conditions, so normal pH and normal temperature, and we call that inhibition. So when we add something, a substance or a therapeutic, that interacts with the enzyme and slows down its activity, that is called an inhibitor. And there are two classes of inhibitors. There are irreversible inhibitors, which destroy the activity of the enzyme by destroying the enzyme itself. So you can't reverse it. You can't dialyze away the inhibitor. The inhibitor is usually covalently modifying the active site. Or you can have reversible inhibitors that bind non-covalently that can be dialyzed away and restore the enzyme activity. Okay, so enzymes can be inhibited irreversibly or reversibly. Penicillin is our example of an irreversible or suicide inhibitor, and we'll look at that on the next slide. So penicillin's substrate is this bond right here, a peptide bond of a lactam ring in the peptidoglycan layer, the cell wall of a bacteria. And so the bacteria needs to be able to build its cell wall, including this magenta peptide bond, okay? So penicillin actually binds to the active enzyme. The enzyme has an active site, serine. We've seen that before. And the serine, which is a nucleophile in its normal role, attacks the carbonyl carbon and forms this ester linkage right here, which is irreversible. And so the enzyme is irreversibly inactivated. So that's our example of irreversible inhibition. Now for the rest of the inhibition section of chapter 12, we're going to be focusing on reversible enzyme inhibitors. And reversible inhibition can be distinguished from irreversible inhibition using dialysis. Remember dialysis all the way back in chapter 2? We use dialysis in chapter 5 also to remove small molecules like salt during protein purification. And likewise, these small molecules that are reversible inhibitors can be dialyzed away from enzymes if you put them in a dialysis bag and then in a large container with a dialysis solution. The next morning you come back and you check for enzyme activity, and if your enzyme activity has gone up, then you were able to dialyze away the inhibitor, and that way you know you have a reversible inhibitor. So that's the first thing you want to do before committing a lot of time and material into doing enzyme kinetics to determine what kind of inhibitor you have. Because you can get an enzyme kinetics reaction that makes it look like one of the reversible inhibitors, but really all along you had an irreversible inhibitor. So you want to do the dialysis step first to distinguish which class of inhibitor you have. Irreversible will not dialyze away, and the enzyme activity will be dead in the morning. Reversible will dialyze away, and the enzyme activity will be restored in the morning after dialysis. Okay, so the next morning you come in, you measure your enzyme activity with an assay. It is restored, so now you're ready to start figuring out what kind of reversible inhibitor you have. And there are 4 classes of reversible inhibitors, so let's look at those. Those are all listed here. There's competitive inhibition, non-competitive inhibition, mixed non-competitive inhibition, and the annoyingly sounding different but almost the same uncompetitive inhibition. Okay, so those are the 4 types of reversible enzyme inhibition. All right, reversible. Remember, we're looking at an enzyme the next morning after dialysis. It was active, and now we're ready to perform some Michaelis-Menten analysis on this inhibitor. Now, this table I took from a different text, and I don't want you to memorize it, but it helps to summarize what's going on in these 4 different types of inhibition. This is a good slide for studying for the test, but we're going to break all of this down in the upcoming slides. So competitive inhibitors, all of these are reversible inhibitors, but competitive inhibitors are characterized by a raise in Km with no change in Vmax. So when you look at the table, the top is your Michaelis-Menten kinetics, there's your Km for Michaelis-Menten kinetics, and your Vmax. Okay, so that's in the absence of the inhibitor. Now, if you have an inhibitor present and it's a competitive inhibitor, you're actually going to be changing the Km, all right, but you're not changing the Vmax. You don't need to memorize each of these different apparent Kms and apparent Vmaxes for the different types of inhibitors, but I would just want you to see that what characterizes competitive inhibition is that Vmax is the same, but Km has been raised. It's you have to add a component to your Km. So we're going to increase Km or raise Km. All right, that's competitive. Non-competitive inhibition is characterized by a decrease in Vmax with no change in Km. Okay, so let's look at that on the table. Non-competitive inhibition, which has a different rate equation because of the presence of the inhibitor, has an unchanged Km, but a change in Vmax. In fact, look at it's the denominator that's increasing. So that means you're going to be decreasing your Vmax. Okay? So that's what characterizes non-competitive inhibition. Mixed non-competitive inhibition alters both Km and Vmax, which you can clearly see here for mixed non-competitive. And so does uncompetitive. It alters both Km and Vmax, but you can distinguish between uncompetitive and mixed non-competitive because only uncompetitive keeps the same slope. So Km over Vmax stays the same only for uncompetitive. Okay, so what does all of this mean? This is just a lot of words and tables and numbers and equations. So we need to actually look at these to understand what's going on. Remember, we're going to be talking about reversible enzyme inhibitors. Okay, competitive inhibition is a type of reversible inhibitor that binds to the same site as your substrate. It binds the active site. And so what's going on here is your enzyme plus substrate goes to enzyme substrate complex, goes to E plus P, is shown horizontally the way you would see it without an inhibitor. The inhibitor, which is shown as I, competes for the enzyme with the substrate. So the inhibitor and the substrate are in competition for exactly the same site. So that means at any given time, in the presence of the inhibitor, some of the enzyme is unavailable for making the ES complex, right? It can't go there because it's bound up by the inhibitor. So if they're competing for the same site, then that's competitive inhibition. When you use a Lineweaver-Burke plot to distinguish between the types of inhibitors, we're going to be reviewing this y equals mx plus b form of the Michaelis-Menten equation. So I just wanted to show you that again. And remind you that what we're going to be looking at is the reciprocal of the initial velocity on the y-axis, or the reciprocal of the substrate concentration on the x-axis, and then the very handy intercepts, right? So now we're going to be looking at 1 over Vmax changing, 1 over Km changing, or the slope changing, or not, right? Because these highlighted terms are what are going to help us distinguish between the types of inhibition. Okay, so we're going to start with the competitive inhibition, and we're going to look at how these terms change on our kinetic analysis in the presence of an inhibitor. Okay, so back to competitive inhibition. We're looking at the intercepts, and we're looking at the slopes, which are just shown by how steep your lines are, right, your slopes. Okay, so the slopes are obviously changing, and the x-intercepts are changing, which means that the km's are changing, but the Vmax is staying the same, so your y-intercept is staying the same, right? That is the hallmark of competitive inhibition. Now, when we look at the numbers, this is a negative number. This would be, let's say, negative 10 for 1 over minus 1 over Km, right? This one could be minus 100, and this one could be minus 1,000, right? So as you're adding inhibitor, you are increasing minus 1 over Km, okay? So that's what's happening as you increase. So alpha 1 is your first experiment with a low concentration, or this is actually no inhibitor. So minus 10 is 1 over minus 1 over Km. Okay. These 3 points. In the absence of inhibitor, you have this larger number, minus 1 over Km, and then your numbers continuously get smaller as you get a larger negative number. Okay, so you're actually increasing the apparent Km. It's a little counterintuitive, but remember it's 1 over Km, and then it's the negative number. So a larger number would be a smaller Km, and the smaller number over here would be a larger Km. I hope that made sense. We'll have to put some numbers in and look at it. Okay, so we know from our first slide that competitive inhibition is characterized by the same Vmax and an increased apparent Km, and that's what this dot is showing right here. What would the Michaelis-Menten plot look like? Well, if you have, so this is a Michaelis-Menten plot, so we're just doing straight substrate concentration and initial velocity. In the absence of the enzyme, you go up to Vmax, you approach Vmax, And in the presence of the inhibitor, you're going to be increasing the apparent Km. So if the first Km is here, this is Km, but you're going to be increasing Km, so that means you're going to be have a larger number here, then your Km is still going to be at 1/2 Vmax. This is Vmax up here. Then the plot is going to look like this, right? Where it's going to take more substrate to reach that Vmax. Okay, so you're still going to reach Vmax, but it's going to take a whole lot more substrate. Why does it take more substrate to reach Vmax? Why is your Km increased? Because you're competing with the inhibitor for the active site. Eventually, you can reach Vmax if you can add so much substrate that you swamp out the inhibitor so that every empty enzyme, once you've gone on to make product, is now more likely to encounter a substrate than it is to encounter an inhibitor. That's competition. So if you can outcompete the inhibitor by adding much higher substrate concentration, then you know you have a competitive inhibitor. So go back here. If you have a much higher substrate concentration, then the big arrow is going to go in this direction, right? And you will win. Your substrate will win, and you will reach Vmax. Because this will be much lower compared to the much higher substrate concentration. Okay? So this only works for competitive inhibition. Only competitive inhibition can be competed, where the inhibitor can be competed by the substrate. So here's an example of a competitive inhibitor. Many inhibitors that are therapeutics are competitive inhibitors. They resemble the transition state for the enzyme, and so they bind the active site. This one is a cyclic GMP phosphodiesterase inhibitor, sildenafil citrate, which is meant to resemble the substrate. So the cyclic GMP is the substrate for this phosphodiesterase. And this is the inhibitor that they came up with that binds to the active site and competes with the real substrate. But it turns out that this phosphodiesterase, which was made for cardiac problems, had a surprising side effect because it produces an increase in cyclic GMP, particularly in the vascular tissue of the penis, allowing the muscles to relax and improving the blood flow. And so that's how we got Viagra. All right, so that takes us to pure non-competitive inhibition, which will be the subject of our next video.